Human language is a fluid, continuous stream of information, but to process it, neural networks require strict, discrete numerical constraints. If a model reads text character by character, the resulting sequences become immensely long. These long sequences quickly overwhelm the quadratic limits of the transformer's attention mechanism, bringing computation to a halt. Parsing at the word level solves the length problem, but creates an unmanageable explosion in vocabulary size. This leads to massive embedding matrices and out-of-vocabulary failures. Out-of-vocabulary, or OOV, is an error state where the model encounters a novel word not present in its training data, forcing it to generate a useless unknown token. The industry default is a compromise known as subword tokenization, specifically Byte-Pair Encoding.
Byte-Pair Encoding, or BPE, is an algorithm that balances sequence length and vocabulary size by breaking rare words into smaller, recognizable chunks while keeping common words intact. To test how efficiently BPE compresses text, we can look at a controlled empirical trial utilizing the complete public domain text of Lewis Carroll's Alice's Adventures in Wonderland. The experiment evaluated a custom whitespace-level regular expression script against the massive pre-trained GPT-2 BPE tokenizer, which contains a vocabulary of over 50,000 units. The outcome was counterintuitive. The advanced GPT-2 model produced an inflated sequence exceeding 52,000 tokens. Conversely, the naive whitespace script successfully compressed the exact same corpus into fewer than 40,000 tokens. This table shows the empirical results, comparing total output tokens, vocabulary sizes, and compression ratios. The data reveals a clear compression deficit for GPT-2 BPE, which achieved a lower ratio of 3.17 characters per token compared to the whitespace tokenizer's 4.28. The assumption that BPE is mathematically optimal for sequence compression is empirically flawed. Locating the point of failure requires looking directly into the internal mechanics of the algorithm. BPE operates through a greedy, bottom-up training sequence. It merges adjacent symbols based purely on their highest frequency of co-occurrence across a given corpus. This diagram illustrates the iterative BPE merge loop. The system tallies individual characters, like U and G, merges them into a functional subword, and permanently adds that new block to the vocabulary to be paired again. To avoid unmapped characters, OpenAI introduced byte-level preprocessing. Byte-level preprocessing, or BBPE, is a technique that locks the base vocabulary to exactly 256 UTF-8 bytes, guaranteeing universal coverage and mathematically eliminating the unknown token. The anomaly in the Alice in Wonderland experiment stems directly from the highly specific regular expressions applied during the pre-tokenization chunking phase, before any merging even occurs. OpenAI's early tokenizer architecture made a specific design choice. It explicitly left consecutive whitespace characters unmerged. This diagram shows a block of indented Python code to illustrate the whitespace pathology. Because of the regex rules, a sequence of 8 leading spaces meant for simple formatting is parsed as 8 entirely separate, identical tokens, devouring valuable space within the context window. A secondary inefficiency arises from spatial prefixing. The tokenizer maps a word with a leading space to an entirely separate, redundant embedding vector than the exact same word appearing without a space. Because BPE prioritizes global frequency, it arbitrarily fractures unique local syntactic structures. A possessive proper noun like Alice's is split into smaller, isolated subwords rather than being preserved as a single unit. BPE's failure in raw sequence compression is not a mathematical bug, but the result of hard-coded historical regex choices that consume the model's finite attention window with empty space and fragmented syntax. Beyond theoretical inefficiencies, BPE's frequency-based logic actively creates cognitive blind spots in modern consumer AI systems. This is highly visible when advanced models fail trivial character counting tasks, such as determining the number of R's in the word strawberry. The word strawberry is sliced into the integer chunks straw, and berry. The pre-processing pipeline chunked the string into opaque blocks before analysis. Because the internal character composition is abstracted away, the network remains structurally blind to the constituent letters inside that final block. This structural blindness extends to the severe degradation of mathematical reasoning. BPE merges numerical digits based purely on how frequently they co-occurred in the training text. This results in highly inconsistent chunking. A highly frequent 3-digit number remains a single cohesive token, while a slightly less common 3-digit number is arbitrarily fractured into 2 or 3 separate pieces. Unpredictable numerical fragmentation misaligns mathematical place values within the attention window. This cripples the network's ability to generalize standard rules for carrying and multi-digit addition. Tokenization dictates exactly what a neural network can process. The specific algorithmic boundaries it draws dictate what a neural network can see and logically process. The structural flaws of BPE also extend to global linguistics, creating an economic and computational disparity known as the multilingual token tax. Because frontier models are trained on corpora heavily dominated by English, the algorithm allocates the vast majority of its finite vocabulary slots to English stems and morphemes. Underrepresented languages and non-Latin scripts rarely possess whole word tokens. The text is forced into highly fragmented byte sequences, instantly inflating latency and API pricing for non-English users. If BPE is flawed, biased, and inefficient at compressing text, the logical question is why the industry has not replaced it with a mathematically perfect compression algorithm. Classical compression algorithms natively exploit linguistic probability to reach theoretical bounds of data density. A 2024 Ablation study from Harvard and MIT tested this directly using the PathPiece tokenizer. PathPiece is an ultra-compressor mathematically guaranteed to find the absolute minimum token sequence to represent any given document. This diagram compares a standard BPE frequency tree on the left with the PathPiece directed acyclic graph on the right, which charts the shortest possible path through a sequence to prioritize raw mathematical density over frequency. The empirical results of the study were highly disruptive. Language models trained on the maximally compressed PathPiece sequences consistently underperformed models trained on standard BPE. Blindly optimizing for the minimum token count generates highly idiosyncratic boundaries. The algorithm aggressively combines the ends and beginnings of completely unrelated words, obliterating actual semantic meaning. The efficacy of tokenization relies heavily on linguistic alignment, not raw mathematical density. Neural networks require morphological coherence to map deep reasoning. Recognizing the cognitive blind spots and multilingual biases of BPE has led to a reevaluation of the foundational role of the tokenizer. One major revision is SuperBPE. SuperBPE is an algorithm that aggressively expands the definition of a token by abandoning the long-standing rule that tokens cannot bridge whitespace. Multi-word expressions function cognitively as indivisible conceptual units, yet standard BPE artificially fractures them simply because a space character is present. This diagram illustrates how SuperBPE explicitly relaxes these pre-tokenization boundaries. It allows the merge loop to fuse highly frequent multi-word phrases directly into singular superwords. The empirical gains of this approach include a 27% reduction in inference compute, alongside significant benchmark improvements driven by a more uniform semantic density across the sequence. Another approach bypasses the tokenization pipeline entirely in favor of end-to-end neural parsing. This is achieved by the Byte-Level Transformer. The Byte-Level Transformer, or BLT, is an architecture designed to consume raw UTF-8 bytes directly from the data source, entirely eliminating static vocabularies and fixed embedding matrices. Processing millions of individual atomic characters historically resulted in a massive computational bottleneck, but BLT bypasses this quadratic scaling penalty entirely. This diagram shows a continuous stream of raw hex bytes flowing into a specialized local encoder. The encoder dynamically brackets the sequence into variable length patches based on the internal entropy of the data before passing them up to a global attention layer. BLT scales computational efficiency by adjusting this dynamic patch size, rather than expanding a static vocabulary list, successfully neutralizing the multilingual token tax and eliminating out-of-vocabulary fragility. As these local encoders learn richer, more complex representations of byte sequences, rigid algorithmic compression scripts will become obsolete. Linguistic discretization served as a temporary engineering compromise. Current research suggests a move towards systems that process the raw, unbroken stream of human language directly.